Welcome to a new session of electrical machines. In today's class, we are going to see the basic E.M.F equation of a transformer. And this particular class, we are going to treat as class 1, where you can see we'll have a constructional details, how the windings are done on the transformer, and we'll derive the E.M.F equation. So before going to the transformer equation, first of all, we should know what is meant by a sine wave and what are the things which you can derive from a sine wave. So this indicates the sine wave in the terms of flux, where flux is alternating and it is varying along with the time. So you can see you have a 0, you have a t. 0 is the reference where the flux is starting. The flux uh, normal value is taken on y-axis and it is varying along with the time t. So you can see the positive flux is equal to the negative flux for a perfect sinusoidal nature. So the total time period for this particular cycle, that is from 0 to, but that is the positive half and negative half when they are equal, that we are treating as time period as t, and it is given as 2 pi. 2 pi is the value of t in radians, and in electrical degrees it is 360 degrees. So one cycle is equal to 360 degrees. And for the half wave, that is for t by 2, it becomes 180 degrees, or in radians it will become pi. Apart from this, you should also understand that exactly at this peak value, that is at t by 4, which is equal to the peak value of the flux, it is given at 90 degrees, or technically the frequency and time period are reciprocal to each other. So therefore, this from 0 to 90 degrees, I can take the value as 1 by 4f. So these things you should easily derive by looking to the sinusoidal input. And if at all you term this flux in terms of voltage, then the term changes to voltage, that is the instantaneous value of voltage, which is given by Vm sine omega t. Omega t we are regarding as an angle. Technically it will be is equal to theta, so that the theta will be taken on x-axis for a sinusoidal input, and the maximum value of the voltage for this instantaneous value will be Vm, that is obtained around 90 degrees. So the average value of a sinusoidal voltage is 0 for one cycle. This is the first information you should know. Then average value of sinusoidal voltage for positive half cycle is 2 Vm by pi. Then RMS value of sine wave is Vm by root 2, or you can also make this note that Vrms is equal to 0.707 Vm, and form factor, which is the ratio of RMS value by average value of a sinusoidal waveform, is 1.1. Apart from that, you should also know the relationship between flux density, area, and flux, which is given by phi is equal to B into A. So these are the important information you should know about the sine wave. Anyhow, the single phase voltage in terms of Vm or V, you can see on this particular graph, and similarly the flux waveform diagram you can see in this particular graph. So when you apply this to a transformer, here you can see I have taken the front view of a transformer, and you can look into the side view like this, and uh, the cores are insulated from one each other by the insulating plate in this fashion. In the outer one and the inner one you can see in the directions, and V1 is the supply voltage which you're going to give as an input. Then the winding is formed on the primary side, and the current which flows here, it is I1, and it gives a voltage E1 in this N1 turns. This winding will give you a flux which is linking the entire core, and it is given by phi. And if at all you wind this secondary limb of the transformer and you connect to a load, then E2 will flow, which makes current I2 to flow into a load, where you can measure the voltage across the load as V2. So this is a what you say, you can have this diagram known as the representation of primary and the secondary winding of a transformer, where this is termed as primary winding where you give the input supply, and this is a secondary winding where you connect the windings to a load. So this is the representation of a single phase transformer diagram. or you can simply make sure that all the side view of the transformer is removed, and this is how the diagrams look like. So you can see here N1 belongs to the primary winding, N2 belongs to the secondary winding. And when you give the sinusoidal input voltage as input to the primary of the winding, you can see the voltage, if at all the magnitude is increased, that is, if n number of turns is greater than n2 number of turns is greater than n1 number of turns, then it becomes a step up transformer. And if the voltage is reduced, then it indicates that the secondary number of turns is less than the primary number of turns, then it becomes a step down transformer. So how to derive the equation for single phase transformer? You can see we have taken here the flux wave and given as input to the transformer. Then when this voltage is applied to the primary of the transformer, and alternating flux is set up as I told you, which links the primary and the secondary winding. Then if at all we assume the flux maximum in vapors and F is the supply frequency, then the magnitude flux increases from zero value to the maximum value, and exactly at 1/4 of the cycle, the average rate of change of flux is given by d phi by dt. So it is nothing but phi max by 1 by 4f. So it becomes 4f phi max. This we treat as equation 1. And again we'll continue the equation by calculating the average EMF induced per turn in volts, which is equal to the average rate of change of flux, which is given by E average is equal to 4f phi max. Now this is according to the Faraday's law of Faraday's second law of EMF, that is mutual inductance. That to second law, that the rate of change of flux is equal to the voltage induced in the coil. So if at all you take the RMS value in the name of average value, then the RMS value of the voltage is given by 1.1 into 4 becomes 4.44 F phi max. And if at all you concentrate the EMF equation of the primary winding, then this becomes 4.44 N1 F phi max. And if at all I replace the flux with flux density and area, then the formula goes to 4 on the primary side. And similarly on the secondary side, the formula goes to 4.44 N2F phi max or B max into area. So this is the derivation of EMF equation of the transformer on the primary side as well as the secondary side. So the transformation ratio, you can take in this equation into the consideration, that is nothing but V2 by V1, which is equal to E2 by E1, also equal to N2 by N1, because voltage and number of turns and EMF induced are directly proportional to each other, and that is equal to I1 by I2, and this is given by a transformer ratio known as K. And for the ideal transformer, E1 will be equal to V1 and V2 will be equal to E2. So that's all for today's class. I hope you like this particular session. Please share among your friends and subscribe to this channel for future notifications. Thank you.